1 minute past according to my clock, so I'll suggest we're going to start with the webinar to make sure we finish on time. So Happy New Year to everyone. Happy New Year 2025, and welcome to the third DWL workshop and its webinar series. Today we will run webinar number 4. But before we're going to start with the webinar, as always, I'd like to do a few acknowledgements. Where's my mouse here? So first, I wish to acknowledge the people of the Kulin nations on whose land we are gathered, or at least I am. And I'd like to pay my respects to their elders, past and present. I also like to acknowledge the Australian National Fabrication Facility, who generously sponsors and supports us in running this webinar series and its workshop. Especially Jane Fitzpatrick, you can see her on the top right, the CEO of ANFF. If you'd like to learn more about ANFF, please have a look at the website. Then, of course, I'd like to acknowledge or appreciate all the hard work the DWL Workshop Organizing Committee have put into it to make this webinar series and the workshop happen. Also today, I'd like to say a few words about our sister meetings, conferences, and or workshops. This would be Mabel, EIPBN, and the Thermal Probe workshop in Europe. So thanks to all those meetings and conferences for supporting us, promoting us, and helping share or bringing out the information about our webinar series and workshops. Also, I'd like to quickly emphasize that without Mabel, without the meeting for advanced electron beam lithography, this workshop series and webinar series would probably never have happened. So big shout out to Mabel and inspiring us and helping us promote the event. All right, then today, welcome everyone to webinar number 4, Chemical Fundamentals and Innovations in MRT's Photoresist Portfolio. This webinar will be presented by Anja Voigt and Arne Schleunitz. They are sitting in Berlin. We already said hello to each other. Before I hand over, I'd also like to mention that this is the second webinar which will be sponsored or is sponsored. This is sponsored by NanoVacuum. So big shout out to NanoVacuum. They have sponsored the last DWL workshop and they sponsor us this year again. So thank you very much for supporting this webinar series and the DWL workshop itself. And with this, I'm finished with my introduction. I'm gonna stop share. And I'd like to ask Anja and Arne to please share their screen. And
yes. Okay. 1 second. Yes.
We can see your screen now. Now it's in
Okay,
presentation mode.
Das kleiner machen. Yeah. Okay. Thank you, Michael, for the kind introduction. And thank you for asking us being part of this webinar series. I would like to start with few words about my person. I'm Anja Voigt. I'm since the beginning at MicroResist Technology. I started chemistry at the Humboldt University in Berlin, and I got my PhD years ago. And I started as scientist at MicroResist Technology. Then I became the product manager for the negative resists at MRT, and since 2012, the business unit manager for the Photoresists. I'm responsible to develop materials, new materials, and also for marketing activities and give presentation of our R&D work as well about the products we have in our product portfolio. Yes, thank you again for the that I can be a part of this series, and welcome everybody. I would like to start with the chemical fundamentals and innovations in MRT's product portfolio. The content or the outline of my talk is shortly shown here. Start only few words about our company, then photolithography, some general aspects, proceed with positive photoresist, negative photoresist, some special applications, general aspects of resist processing, FAQs, and a short summary. The first part, let's say, is mainly about MRT products, but trying to dealing the question Michael provided to me in advance, so that there's some new for us, some recap of some things, hopefully, yeah, to meet your expectation for this webinar. Company information. MicroResist Technology is specialized in providing innovative resist polymers, photopolymers, and ancillaries, and we support our high-tech customers with high-tech performance materials, technologies, and process chemicals. We were established in 1993, and we are about 50 employees. We are located in Berlin, Germany, Europe. And so we have a production unit and a clean room. What is important, we are certified according to the quality and the environmental management system. This is very important to our customers, that they know how we work and that everything is well aligned according a quality management system. What are the fields of our business activities? We are manufacturing, formulation, synthesis of materials and products. We have a strong cooperation with partner companies and distribute their products mainly for sure in Europe to complete our product portfolio and to be able to offer our customers the whole bunch of materials for their needs and their requirements. We are doing R&D to develop new materials in funded projects or with industrial partners, and we also for sure have a clean room for the quality check of our materials, but also to develop special lithographic processes according to the customers they ask us. What are the products we have? So MRT has 4 main product groups composed of the negative photoresist, positive photoresist, some kind of hybrid polymers, and nano imprint materials. Today, I would like to talk mainly about the negative and the positive resist and lose few words about the hybrid polymers, which are also negative acting materials. Nano imprint materials we also have in our product portfolio using a different kind of patterning technology. If you're interested to learn more about that, please ask us and we can provide you more information. Just a few words about our distributorship. On the right side, there are information about the companies we distribute mainly in Europe. It's from DuPont Dow, the electronic material with a level packaging materials as well, dry film. Then Kayako Advanced Materials, formerly known as Microchem. They develop and have the SU8 family in their product portfolio, PMGI, LOR, and PMMA. And then DJ Microlaminate, they developed epoxy resin film dry films. And Schleunitz, they offer for a bunch of products, and we distribute from Schleunitz photo-curable PDMS, which fits perfect to our nano imprint materials and can be then used as replication material. So that's very shortly to the MRT, the company. Coming to the next photolithography general aspect. Okay, what is the process in photolithography? You would like to pattern something. very small. Typically, you have a substrate. You need a liquid photoresist to be coated on the substrate. Then it is exposed to light. Light can be UV, deep UV, electron beam lithography, extreme UV, X-ray, or what else. Then you expose it and some kind of reaction is happened. Some photoresists require post-exposure, bake after exposure. Then you apply the development. And depending on the kind of photoresist, the exposed areas are developed, washed away for the positive resist, or for the negative resist, the unexposed materials is developed away. Here you can see the usual exposure energy. The mainly photoresists are used or are exposed by using the UV light, which is divided in UVA, B, C, seeing here the wavelengths area they cover. That's the exposure energy, what's available. And it's very important that the resist have to be sensitive at the lights the exposure tool is emitting. So for the UV, for the mask liner, which are available using either mercury lamp or LEDs, typical UV broadband or broadband sensitivity is required, having a sensitivity between 300 to 450 nanometers for the resists. For UV exposure, also I-line, a single wavelength emission can be used with the LED or a stepper. Also, a laser can be used with a monochromatic exposure, as excimer or a diode laser. It's a direct writing process. Deep UV using wavelengths which emit at shorter wavelengths. E-beam with even higher energy. Also, some kind of different patterning technology can be used. The manufacture of resists. So the photoresist is a light-sensitive material. It's already in the name, so photoresist. The key components are: you need a polymeric binder, a resin. It can be a different resin. I will talk about later about the type of the resin. But this resin is responsible for the layer preparation, to build up a layer in a different thickness, and responsible also for the chemical reaction or the functional group the resin has. That something is happening, you need a photoactive compound, which is added. These two main components have to be clearly dissolved in a solvent, which can be a pure solvent or a solvent mixture. It is selected, the main requirement for the solvent is to dissolve the solid components. Then some additives are added, like leveling agents, adhesion promoters, surfactants, or dye, depending on the photoresist. All these raw materials are mixed until a clear solution is obtained, and then the material is filtered through a syringe filter. Typically, the pore size of the filters, that's a rough formula for that, 1/10 of a thickness. So if you want to have a resist layer of 1 micron thickness, 1/10 of that is 0.1 micrometer pore size for the filter should be used. Photoresist available as liquid photoresist. To sell the liquid photoresist, that's what we are doing. So manufacturing the resist, put it in the bottle, and we sell it worldwide as a liquid in the bottle. Together with the liquid photoresist, also we provide the process chemicals. The main here are, you can see how the liquid photoresist can be coated, or the layer can be prepared on different kind of substrate. The main method to prepare the layer is spin coating, but we also offer materials which can be inkjet printed or spray coated. Also, dip coating, doctor plating are some method to coat photoresist for some substrate which are heavy and cannot be coated by spin coating. I put also here the dry resist film. So we also distribute, and it's also available, dry resist film, meaning that the dry resist is in between two cover foils. As far as I know, only negative acting dry resist films available, and they are provided on a carrier foil with a cover foil as protecting foil. They can come or comes as rolls, or depending on the thickness, if the thickness is rather thick and they cannot be rolled, they are provided by sheets. For what the materials can be used? Yeah, you generate the pattern, and depending on the kind of application, you have to select the right resist material. It can be the permanent application or non-permanent application, which is pattern transfer, which is the most or commonly used method for the use of the generated pattern. For the permanent application, it can be used either a single layer or a double layer pattern generated and then used directly or replicated by somewhat. It can be also covered, and applications could be here for MEMS, micro-optical electronic mechanical systems, waveguide applications, microfluidics, or, as I already told, master for replication. The non-permanent application, there are the subtractive procedure, meaning that you go into the substrate, and here the resist can act as etch mask for wet or for dry etching. Depending on the kind of substrate, for the wet etching, it's mainly an isotropical process, but depending on the orientation of the substrate, you can slightly tune also the etching profile for the wet etching. For the dry etching, depending also on the process, it's more, let's say, an oriented etching process going into the deep. There are additive procedure in use. The most common is that the resist must act as mold for electroplating. So put the resist pattern into an electroplating glass, and some metal is then growing between the resist mask. Also, the PVD and lift-off process is one common process. PVD means physical vapor deposition. It's done by sputtering or evaporation process and typically used for metals or different materials where the electroplating process will not work. This is one reason. And then the resist is lifted off, and finally you get the metal pattern or the etched profile. For the permanent application, nearly in all cases, negative resists are recommended to be used since it's permanent. The negative resist is then cross-linked and mechanical stable. And for the pattern transfer processes, use preferable of positive resist because of the easy removability of the positive resist, but also negative can be used depending on the pattern transfer process. Sometimes the pattern transfer process is very aggressive, and then negative resists are more recommended. Some application examples of the photoresists. So depending on the pattern size, there are a bunch of different applications coming from the MEMS, MOMs, and also waveguides applications or generation of contact pads and small metal parts as mentioned here. Now I would like to come to the positive resist and some application examples. MRT has since the beginning different or various positive resists in our product portfolio. The commonly used not only by MicroResists are the D&Q Novolac resin-based resists. There are also other resists based on the same main chemistry available on the market. For instance, these are from Dow DuPont, the S1800 series, SPR series, or the AZ series. There are different kinds for thin and thick photoresists. The typical absorption spectra of this kind of photoresist is shown here. It shows a high absorption between 300 to 450 nanometers. It's a solid line. And this is the absorption spectra of the unexposed material. When you use the exposure tool, mask aligner or laser, whatever, typically emitting light at the I line, H line, or G line, you can see that the resist perfectly absorbs the light and can react when you use all of these wavelengths in a mask aligner or just using one single exposure wavelength of that. What you also can see here, after exposure, the resist absorption is decreased, meaning the resist is bleaching out. The pack is converted, the photoactive compound is converted into something that absorbs less light. So the dashed dot line is the absorption spectra of the exposed resist. So this is one typical behavior of this kind of photoresist, meaning also that you can expose thick resist films. The light goes from top to the bottom. So, but I will explain later more about that. Yes, these kind of photoresists are available for thin layer applications as well for thick layer applications. Typically for binary, to generate binary patterns, but can also used to generate grayscale pattern. These are the products which MRT has in its product portfolio. They are typically used for dry etching and wet etching process as mask, as already mentioned, for metals. Thicker films also used for ion implantation processes or resist are used as mold for electroplating and for UV molding. What is the composition? Novolac resin, it's a phenol cresol resin, oligomer resin. The aromatic are connected via the methylene group and having OH group. And these OH group are responsible that the material can be developed in weak alkaline-based developer. But you need the photoactive compound, which is a D&Q. It's a diazo-naphthoquinone derivat, which is shown here. The part of that D&Q which is responsible for the chemical reaction is shown here. The backbone is slightly different for the different positive resist, leading also in different residual absorption, and it's a kind of secret for each manufacturer. But the main chemistry is shown here. These components need to be dissolved in a solvent. Some additives are added. This is, aqueous alkaline development is possible, and it's a non-chemically amplified resist, a non-CAR resist, meaning one photon leads to one photochemical reaction. On the right side, you can see the dissolution rate. So the Novolac itself offers a certain, let's say, dissolution rate. Once you add the photoactive compound, it acts as dissolution inhibitor, meaning the dissolution rate is decreased. So it's the resist itself, it becomes stable and is not that easy soluble in aqueous alkaline solutions. Then you apply the exposure light, or it can also be thermally activated. During that, nitrogen is extruded. And one important is that you need for the finalization of the chemical reaction water. And as reaction product, indene carboxylic acid is formed. And this acid is soluble, much more soluble in aqueous alkaline solution than the unexposed area, leading to such difference of the dissolution rate. And what's important, the resin remains chemically unchanged. That's for positive resist, leading that the positive resist are, let's say in nearly all cases, relatively easy, can be removed after pattern transfer process. This is the chemistry, the principle of the chemistry behind nearly all D&Q Novolac resin-based resists. What we have in our product portfolio, the MRT 1200, which is available in a variety of viscosities. So by the use of the different types, you can generate in patterns resist layers between 300 nanometers to 60 micrometer thick films by a single coating process. This is a common process. Use the generated mold for electroplating. In that patterning example, the thick photoresist of a 10 micrometer thickness is used to generate copper pattern in one example, or a gold array electroplated in the mold. So, but a special application is also, some customers want to generate grayscale pattern. And grayscale lithography is applied when standard binary photolithography with the common process does not suffice. Sometimes customers want to have some complex structures such as concave or convex lenses, 2.5D patterns of different height next to each other, or any free-from micro-optical topography. For some grayscale patterns, the summary flow process might be applied. So starting with the binary lithography, generate binary pattern, apply the thermal reflow, and then you have some lens shape pattern, which can be then used to transfer underneath into the substrate. Typical lens shape or micro-optical lenses are generated by having this process on a glass substrate and then using the etch process under the to transfer the lens shape pattern into the glass substrate underneath. But the other kind of 3D pattern cannot generated via this process. For that, grayscale lithography is recommended to be applied. And for that, it is recommended to use a low contrast positive resist. That also for the binary lithography, you want to have a clear difference between unexposed and non-exposed areas. And for the grayscale, you need a defined small difference in the different applied exposure dose. And here, a low contrast is an advantage. But how grayscale pattern can be generated? There are two methods. One method is laser direct writing. You have the positive resist layer, and then you expose it by laser direct whiting by applying different doses. The same can be done also with a mask liner, having the emission spectra. But here you need a mask, and the mask is not a binary mask, it's a grayscale mask. Grayscale mask means that you have areas with non-chromium on top, fully 100% density of chromium, and something in between. So some pixelating, having a different density of the pixelated chromium dots, allowing to have some kind of a dose level in between. This is then used with mask liner lithography, and after the development, the different dose or the dose gradient resulted in a pattern gradient. Yes, the laser direct writing process is a rather time-consuming process because it's a direct writing method, but it's a very accurate process, the correction of proximity effects, and may change in non-linear resist response by adapting gray value distribution is easily possible. For the mask liner based process, it's a fast process, just one shot, and you have the whole substrate exposed, but it's typically a two-step process. So you have the resist, you need the contrast curve, have first the first mask, and then generate the final mask according the determined contrast curve. And then, but once you have the two-step process, you can very fast proceed to generate the grayscale pattern. For this series, MRP 1200G, we have also different viscosities available, starting from very thin layers and up to very thick layers. Up to 70 micrometer thick films can be obtained by a single coating step. And the maximum obtainable grayscale exposure depth is about 55 to 60 micrometer in depth. So how it works? For thick resist layer, it's very clear. You deposit in thick resist films different kind of doses. And according to the absorption spectra showed you before, only small amounts, or according to the applied dose, is converted into the higher solubility material. And after development, finally, you get the grayscale profile in the resist. But how it works in the thin layers, you can imagine the resist layer is very, very thin, and the light goes through at any time. But the reaction mechanism behind here is that the numbers in the whole layers of converted PEG, photoactive compounds, is different, finally leading in different dissolution rates in the developer, leading to a grayscale profile after development. Yes, the generated patterns are still light sensitive, so they need to be replicated or transferred into a stable material to finally have a stable grayscale pattern. Here I would like to show you some examples generated by laser direct whiting of using MRP 1200G, having a resist thickness of about 50 to 100 micrometer. A laser direct whiter at 405 nanometer were used, and you can see the very smooth and well-defined grayscale level. But you also can see that besides the grayscale level, also very sharp binary patterns can be generated as the customers or the application, according to the application's requirements. We also applied the grayscale value level used by Genesis. But this cannot only used in thick layers, it can also used in thin layers, which is slightly more challenges. But here's an example where a 500 nanometer thick layer of that resist type is used to generate steps of 20 nanometers by laser direct writing using that tool. And this step size pattern is then transferred by reactive ion etching into the silicon substrate underneath. So can be used for thick and for thin layers. Here is an example where mask-based grayscale lithography were applied by using mask aligner and a grayscale mask. On the first picture, we used a pixelated mask having chromium dots in the mask, having a different density of the chromium mask provided by Benchmark. This is a commonly used type of grayscale mask for the photoresist, and here's an example of a resist thickness of 30 micrometer shown. And there are other kind of grayscale mask available using the HEPS mask. The HEPS mask means high energy beam sensitive glass mask. The glass mask is generated, so you have a glass. There is silver ions in, and when you expose the glass by E-beam, the silver ion converted to silver, which makes the glass dark, let's say, and reduce the transmission. And by using that, you can clearly fine-tune a very smooth gray level into this kind of mask. So no chromium on top, as for the other one. It's directly into the glass, the gray level generated. And we're also having this kind of mask and tested for this resist. And this is an example shown where this gray level mask is used to expose this photoresist. The provider for this mask is Canyon Materials. So these kind of different masks are available. Besides the mask aligner lithography, also, eyeline stepper lithography can be used. Also for that, Benchmark typically provide the reticle, let's say, mask for the eyeline stepper exposure in grayscale level, where an example is shown here. This material can also be patterned by laser interference lithography, where some kind of gratings is exposed into the layer, also leading to some kind of grayscale level. In this example provided by our partner Temicon, the same resist is used and laser interference at 351 nanometer they are applied in a resist layer having a thickness of about 3 to 10 micrometers. And the gratings which are obtained, the pyramid gratings have a height of about 5.6 micrometer in height and are very regular. In that specific example, this generated master were then replicated by electroplating. First apply a seed layer, a metal seed layer, and then by electron process generates a nickel shim, the nickel master, to for an application. We also have a white paper coming out, and if you are interested, you can read it and directly download this paper about the grayscale and generation of 2.5D structures from our homepage. This is then a pattern example also for the resist. Here, the hemispherical solid immersion lenses and silicon carbide were generated. So you have a resist spin-coated and a rather thick layers at 8 micrometer, then grayscale exposed with a laser direct writer, and then pattern transferred via a dry etching process under the substrate underneath. And this is then as hard mask used to finally pattern the silicon carbide by a dry etching process underneath. This is by fine-tuning of the etching condition. Typically etching selectivity is 1:1, but you also can tune the etching conditions to finally have different from that etching rates leading to not any kind of shape of lens, but yeah, to slightly adapt the shape what you want to have for your application. So for thin resist, typically the etching is a commonly used transfer process. But you can imagine once you have rather thick resist layers, about 60, 80 micrometer as master for the grayscale, that the etching becomes more, let's say, challenging, meaning leading to an increase of the temperature, and it would take more time. And an increase of temperature for the positive resist could be critical because pattern resist distortion could be observed. For that, other pattern transfer methods are tested or recommended to be used. Here you can see first the resist mold, and the resist mold can be then replicated thermally with PDMS, just pour PDMS on top, cure it, peel it off, and then you have, let's say, non-light sensitive stamp to generate for several times the permanent pattern. In that application here, the PDMS is used for UV molding with a hybrid optical polymer, in that case Omocom. Or you can have the positive resist pattern as master and direct pour the hybrid polymer on top and apply or cross-link by UV molding. In any case, for that, the positive resist pattern needs to be dissolved or is dissolved to finally have separated the Omocam pattern. Or, as already shown, you have the resist masters, apply a thin seed layer, doing the electroplating, and then separated the metal replica from the positive resist master, which then can be used for UV molding or of other polymer which you want to have for your application. All these pattern transfer methods are possible. The first one could be the favorite because it's a non-destructive for the generated master. It's up to you what you want to do as for the application. Challenging still, you have to keep in mind the master is still light sensitive, and so any long or any high thermal treatment could be critical. So that's why we would recommend to use the first one, the non-destructive pattern transfer process. Otherwise, resist pattern distortion could be possible. As already mentioned, with the MRP 1200G, resist thicknesses up to 70 micron can be obtained and pattern generated. The question is, can we go even thicker for the grayscale resist? And we can clearly say yes. We have developed a new experimental material, MRP22G, as XP. By using that, you can obtain a 130 micrometer thick layer by a single coating step, or up to 200 micrometer thick by a double coating step. This is one, but the resist formulation was adapted and the photoactive compound tuned, allowing that the residual absorption after exposure is much lower than for the MRP 1200G. And here on the right hand, you can see the light attenuation. It's calculated by knowing the absorption coefficient at certain wavelengths. And this gives you an idea of, about light attenuation at different wavelengths. And by using a 405 nanometer laser exposure light, it's a red line, you can see that's in principle possible to expose up to 200, let's say 180 micrometer thick layer in depth. And what I can show here is that we successfully generated a layer of a 200 micrometer thick of that material. And this pyramids pattern often an exposure depth of about 155 micrometer in depth. So finally, I can say yes, it's possible to generate such deep pattern. The second picture shows also some real pattern generated in MRP 22G, having a depth of about 130 micrometer. And we use that generated pattern for replication purpose, and that we replicated as with PDMS, the thermal molding, put PDMS on top, cure it at gentle temperature for 48 hours at 35 degrees Celsius, peel it off, and then use the PDMS mold for UV molding of an, let's say, optical polymer for final curing. And by testing the accuracy of the generated pattern, we found that only 2 to 3 micrometer film thickness loss in total. So the patterns are very accurate transferred into the final optical polymer. I would like to proceed now with the negative resists. From the negative acting resists, we have in our product portfolio, let's say more than one type. One type is the MAN Novolac resin-based. Novolac similar to the positive resist. Then we have the epoxy resin-based. And some special kind is the hybrid polymer. All these materials cross-link when exposed. We have materials, or there are also from other providers as epoxy resin-based materials available. They are provided for thicknesses below 1 micron, and for some materials also to very thick layers. It's typically used for binary lithography. I would like to start to explain more about the MAN Novolac resin-based resists. What is the composition of the MAN resists MRT is offering? Here also the resin, the polymer matrix, is a Novolac, which makes this kind of resist also developable in aqueous alkaline solutions. As photoactive compound, which is required, it's a different. In that case, it's a aromatic bis acide. So you have the aromatic group, which are connected via an X with the secret. And for the chemical reaction, you need the acids on both sides. And after exposure, nitrogen is also generated and radical is generated, which connects or reacts with the Novolog. All these components are dissolved in a solvent or solvent mixture. It depends, and some additives such as leveling agents or whatever can be or is added. Aqueous alkaline development I mentioned, and again, it's also a non-chemically amplified resist material, meaning one photon leads to one chemical reaction. So that means that you also need a slightly higher exposure dose than for the chemically amplified resist, but yeah, no problem. What kind of materials MRT offer? So we have the MRN 400 and 1400. The absorption spectra is shown here on the right side. The solid line of each one is the UV spectra of the unexposed. The dashed line is the UV spectra of the exposed line. The main sensitivity is at UV I line, 365 nanometer. And the pattern transfer, let's say, similar as for the positive resist, so for dry and wet etching. But the specific properties is here. It's recommended to be used for physical vapor deposition and lift-off. Why it is used? You can see the material is not bleaching out when you are exposed. There are some reaction product generated absorbing also light. So you can imagine you have the resist layer, you expose it. On top of the resist layer, the material is fully cross-linked, and the cross-linking degree coming to the bottom near the substrate is less. Why it is so? The light is catched still on the top and less light goes to the bottom, leading during the development in an undercut pattern profile. This is obtained for both series, according also to the UV spectra. And here's an example for 2 micrometer thick layer. By applying the recommended exposure dose and just by prolonging the developing time, you will clearly define the undercut profile. And depending on developing time, your undercut is generated, also the size of the undercut. Here are some other examples. You can clearly see the density of the crosslink material is very, very good. And yeah, underneath it's then developed. The undercut is generated and developed away. This also results in that there's a limitation in thickness you can expose. Available thickness up to 10 micrometer. We also have some application where 15 micrometers can be patterned, but even thicker is not possible because it's clear too low cross-linking degree near the substrate and it's then washed away. But this material is very stable and clearly used for PVD application. This material is let's say a very well introduced material for various PVD and lift-off applications. Here in a lift-off application for both resist materials is shown. A thin gold sandwich layer is evaporated on a titanium wolfram pad. Then the resist is removed. By looking on the thin gold sandwich layer, you can clearly see the sandwiches or the different layers. And by applying a reflow process, this metal mixture is then reflowed, offering a harder core than a softer shell, allowing that these generated bumps can be used for flip chip bonding. Typically, also by the use of this kind of resist, 3 metal contact pads are generated, or some kind of mirrors based on aluminium or silver are generated. These resists are used for thin and also for thick application. On the right side, MAN 1400, which is offering a slightly higher thermal stability, sometimes required when thick metal layers have to be generated. The resist which was used was about 7 micron, and here metal layers, different composition, up to nearly 6 micrometer were generated successfully. And this material is very well introduced in production. This material offers the chemical stability also for electroplating processes. Here's an example there for nickel and gold shown, but you have to keep in mind you have nearly always a slightly undercut. Actually, we had a customer who was interested to have that not vertical metal pattern. They wanted to have some kind of trapezoidal pattern electroplated in that kind of resist. And the chemical stability is also given if you want to have it for dry etching processes, as shown here. I mentioned main pattern transfer is via physical vapor deposition and lift off. You may keep in mind that there are also other possibilities for PVD and lift off. Beside the single layer negative resist system we offer with the MAN 1400 and MAN 400, there's also a B-layer system in use, let's say. The B-layer system is mainly composed, for sure, on two layers. The first layer is a non-sensitive LOR or PMGI layer, just coated, baked. And then you have the mainly positive resist on top. And by developing the positive resist on top, the LOR layer underneath is dissolved also with the same developer, generating some kind of undercut. And why customers are using the B layer or the single layer system? I think it's mainly for historical reason. Sometimes they also want to have a specific undercut profile. The undercut profile for the step 2 layer is more a step size undercut. For the negative, it's a diagonal or an S-slope, depending on the application. And sometimes also the thermal stability could be an issue or a question the customers having taken care or keep in mind. And according to the requirement of the application, they select the right material, either the single layer negative or the bilayer process. By the way, you can also put on the LOR a negative resist, just if you have a negative tone mask. Okay. And for clean lift off, it's recommended that the resist thickness is 1.5 to 2 times higher or thicker than the generated metal layer. That, the resist stack with the metal on top is clearly lifted. Now I would like to proceed also with the negative resist, with the MAN resist. MAN resist 2400. The main chemistry behind is the same, except of the aromatic bisaicate, it's a different one. And this offering a sensitivity at lower wavelengths. So the MAN 2400, it's a deep UV and E-beam sensitive material. It's mainly used for sure for thin layers and used for pattern transfer processes via dry etching. Actually, in the example here, dry etching application is shown. They have a rather thin layer on top, which is a resist layer, is used as dry etch mask to etch silicon underneath in the substrate. By fine-tuning the plasma etching condition, it's allowed, you can tune the etch selectivity, and it's a really, really high etch selectivity, which can be obtained here. For sure, etch selectivity is 1:1 for nearly all cases, but can be fine-tuned to 1:10 or even much higher. Some customers also ask us, can the material or the resist be used for dry etching processes at lower temperature for cryonic etching? That's always challenging because of the harsh temperature difference from room temperature to low temperature. That's no cracks, so it should be a ramped process. And in that papers here, you can read more. It is shown that the resist also can be used for cryonic etching. In that application, it was minus 120 degrees. And the etching selectivity was about 1:10 for this kind of resist. But some customers want also to not only their dry etching, they also want to do the lift off once they have generated the patterns via electron lithography. And here is a paper mentioned, an example given, where the same resist is used. One paper, two different processes. One process is a lift-off process where chromium gold markers are generated via lift-off process. And after that, in a second process, again, the MRN 2400 resist was coated on top and then used as dry etching mask for finally generate silicon nitrogen waveguide device. And the last example I would like to show is a rather, let's say, unusual example, the use of the material for permanent application. So in that, some kind of meta surfaces were generated. And they were not generated only in the resist. The resist thickness was about 2 micrometer, and you can clearly see here that's no footing and a high aspect ratio patterns can be generated. And here itself, the resist layer was used as meta surfaces because of the sufficient light and thermal stability and the refractive index which fits. You can imagine it's a rather expensive method. The ideal case would be then replicated use that as master and replicated in a different material. But that shows that the material itself is possible or can be used to generate such kind of patterns. Now I would like to proceed with the second negative resist, the epoxy resin-based resist, where also MRT has some materials. What does it mean, epoxy? Epoxy means that you have some kind of polymer having the epoxy group. This is a formula of the schematic of SU8. SU8 resin, it's an ideal formula. Typically, it's not only SU8, it's a shorter and a longer version, and not every group is epoxylated. But in principle, you can imagine it looks like that. Important is that you have the epoxy group there. There are also aromatic, aliphatic epoxy resins available, different kinds. That's a resin. but you need a photoactive compound. In that case, the photoactive compound is a photoacid generator. So you have that, which is an aryl sulfonium salt added to the resin. Both materials are dissolved in a solvent with some additives. And how does it work? So after exposure, some proton or acids are generated, and these acids or protons attack the oxygen of the epoxy group of the resin, leading to an opening. And this is then cross-linked to another epoxy, and another proton or acid is released again, meaning that one photon, one exposure leading not only to one acid of one photon, since it's again generated an acid, it's some kind of chemically amplification reaction mechanism. So one photon leading to more than one acids. It is mentioned that the amplification factors of about 50 to 100, depending on the used photoacid generator, is generated. This results that lower the content of a required photoactive compound is lowered than for the other materials, what just one photon is reacting or leading to one reaction. Meaning the epoxy resin-based material are chemically amplified resists. This is one example of chemically amplified resist. And the epoxy resin-based materials are solvent developable. Again, yes, on exposure, the pack generates a strong acid, and this acid attacks the oxygen. And finally, because of the amplification mechanism, after exposure and post-exposure bake, a very insoluble, dense polymer network is generated, which makes the pattern very thermostable, chemically stable, and mechanically stable. Here materials for very thin, below 1 micron, as well as rather thick resist layers are available, typically used for binary lithography. Pattern transfer methods can be applied via dry wet etching, electroplating, and here also for permanent application because of the high thermal stability. What kind of materials are available for these epoxy resin materials? The first one and the well-knowns are the SU8. They are developed and provided by Microchemicals. Now they have renamed its Kayako Advanced Materials in the United States. What types are available? They started with the standard SU8. Then they developed the SU8 2000. And since it's a strongly cross-linkable material, leading some kinds in some stress and crack formation because of the highly dense network, they developed the SU8 3000 version, offering or is a less flexibilized version that less stress and crack behavior. Each series available in a certain range of viscosity for a variety of thicknesses. SU8 and SU8 2000 have the same solid compounds, but the solvent is different. Why it's different? So cyclopentanone offering a higher evaporation, leading to faster drying. That was the idea behind, and that's a flexibilized resist. Since the original SU8 is solvent developable, and customers ask also, yes, is there aqueous-based developable material available? And yes, it is. So the KMPR Photoresist is aqueous alkaline developable, offering same mechanical chemical stability as original SU8. Yeah, but also it's a strongly cross-linkable network. Removability is also challenging. Some customers use the original SU8 for bonding applications. And since the original SU8 versions does not perfect very well for bending applications, Kyaku decided to develop some optimized SU8 materials to be used as bonding. So the Perminex 1000 and 2000 series available, offering in principle same background chemistry, and are more recommended for bonding application, meaning bond resist layer or pattern with a substrate or two substrate, whatever you want. Then some customers are also interested in rather thin layers, and for that, Kyaku decided to develop SU8 TF, means thin film, 6000. The resist formulation is slightly optimized also to give a higher resolution, better adhesion and pattern performance in thin layers. What is available from the MRT product portfolio? So we have the Epocore Epoclet material system in our product portfolio. It's a two-material system and developed for the manufacturing of polymer-based optical, single modes, and multi-modes polymer waveguides. What is required? It needs to have different refractive index for the Epocore and the Epoclet, which is shown on the right side in the picture. It's a 3-layer process. First, you coat the first cladding, then coat and pattern the core material, cover it with the Epoclet. You also can then cover or laminate with the substrate. You finally have the waveguide in. Available thickness or viscosities to obtain thickness from below micrometer to 150 micrometers. And here are some examples shown where these materials are used for the generation of polymer-based waveguides. These are the optical loss value for telecommunication wavelengths, as well for 850 nanometer, where the materials developed for, let's say, for microfluidic devices, where their short distance waveguides advantage. For that, it was mainly developed, but can also used for other applications. And another application is shown here in all polymer arrayed waveguide gratings for fiber grade gratings is manufactured, made from Epocore and Epoclet. The thickness which is used is about maximum 5 micrometer, and the dimension shown is here. And it's an application of who wants to read more can read in the paper, and it's used for optical interconnection applications. As already mentioned, determination of composition of chemical analytes and microfluidic applications, and could be a part of integrated photonic systems in microfluidics. Another epoxy resin-based materials, MDWL. Actually, the development of the material was initiated or done together with Heidelberg Instrument. They offered high power, low expensive or non-expensive diode laser, which emits a light at 4 or 5 nanometer. And no negative resist was available, having sensitivity at that wavelengths. For positive resist, they are available, but no negative resist. And the idea was to develop a negative resist similar to SU8, but offering a sensitivity of 5 nanometer wavelengths. And for that, we developed the MRTWL, which can be used for eyeline, but is mainly used for fast and contactless prototyping by laser direct writing at 4 or 5 nanometers. And thicknesses up to 150 micron, or even thicker, can be generated and exposed. I would like to show you an example here. Where a two-layer lithography with 2 laser emission wavelengths were used. So you have as first layer an SU8. SU8 is exposed at the eye line 365 nanometers. Then you coat the MRTWL on top, expose it at 405 nanometer, where the SU8 layer underneath is not sensitive. Apply the post-exposure bake, and then develop the whole stack, and finally you get some kind of suspended microstructures by the use of these two material systems. This material MRTWL can also be patterned by two-photon polymerization. Two-photon polymerization is some kind of exposure in a volume, in a voxel, in a certain voxel in a resist layer. The ones which were started were nanoscribe, having a femtosecond laser at 780 nanometers, which requires a sensitivity of the material at 390 nanometers, where the SU8 has not sufficient sensitivity, but the MRTWL offers sufficient sensitivity. And here some examples are shown where an MRTWL layer is exposed by two-photon polymerization with femtosecond laser at 780 micrometers. The first pictures are generated in the 30 micrometer thick layers, but the pictures on the bottom are generated in a resist layer of about 500 micrometer. And here you can clearly see the 2.5D patterns generated by two-photon polymerization. So we have that material, and do we have also a material which is sensitive at E-beam? We can clearly say yes. It's named MR-EBL 6000. It's also epoxy resin-based. It's a low viscose material. It's E-beam sensitive and UV sensitivity. It offers a high resolution capability. And since it's a chemically amplified mechanism, the exposure dose is rather low. Here are some patterning examples of the material. Actually, in that application, due to the high thermal and mechanical stability of the generated pattern, it's used here as stamp in nano imprint lithography. This was a curious application, but it's possible. The main application is that it's used for pattern transfer processes via dry etching processes. Do we also have an inkjet printable material from this material group? And the answer is yes. So we solvent modified one epoxy resin material to be inkjet printable. So for that we have different viscosities available, and the customer can select the right viscosity for the right inkjet printing tool. And the same properties as for the other epoxy resin materials, so high thermal, mechanical, and chemical stability. Since of it's, let's say, transparent, nearly transparent material, slightly yellowing it material can also be used for optical application, depending on the wavelengths. And here are some applications shown. Yeah, it can be used as for permanent application, micro lenses or a spacer or protecting layer, or as glue for bonding applications. And depending on it can be coated by several nozzles on the substrate to have a whole layer, or also inkjet printing is a material saving method for direct patterning. Just deposit the ink where you want to have the pattern. Direct patterning method. And also the shape of the pattern can be shaped or treated or controlled by applying surface treatment. Then the lens is more a lens shape. Is it then more a half spherical shape, or is it more a flat lens shape? And also, once you have the substrate pre-patterned, just deposit on top of the patterned of the pattern. You finally can shape the deposited pattern. So here's some kind of ring pattern, and non-spherical lens are generated. And the question is, are there also dry resist films available? And the answer is yes. DJ Microlaminate is one of them. They developed epoxy resin-based dry resist films, and the names are ADEX and ZUEX. The material comes, as already mentioned, in sheets, available in sheets or as rolls, where the dry resist film is in between some foils. Available sheet sizes and roll sizes are mentioned here. For the ZUEX, the same developer as known for the SU8 can be used. For the ADEX, solvent needs to be slightly changed. How it is applied? So you have the dry resist in between, you remove the cover foil, then you laminate it by a certain pressure and temperature on a planar substrate or a substrate having a certain topography. Then remove the protecting foil, expose the dry resist, and then develop. So it's a rather it's a rather fast process, especially when thick epoxy-based resists are wanted to used. And on the right hand, there's an example for multi-layer and multi-patterning process. Some kind of gear of different sizes are applied by multi-lamination, exposure, and just one development step at the final end. With this, I would like to skip to the third group of negative cross-linkable material, to the hybrid polymers. Hybrid means, something in between. You have inorganic and organic. Inorganic is the silicon dioxide skeleton surrounded by organics. The organics makes the material cross-linkable. And finally, after cross-linking, you have an inorganic-organic network generated. It's a radically mechanism. It's, let's say, also chemically amplified. So radical means you generate one radical after exposure. It cross-linked, and again, a radical is generated, which leading to further polymerization. Due to the inorganic part of the material, which is silicon dioxide, the material offers a higher thermal mechanical stability as well, which is for optical applications very important, a higher optical transparency. Yeah, developer is solvent-based. So this material offering a high thermal stability, and here you can see how it looks. So it's rather clear. So the polymer itself, it's inorganic silicon dioxide, not that colored. This material can be patterned by direct imprint, meaning UV molding. You have your mold, press it in, cure it, and release the mold. It is also sensitive for 2-photon polymerization at femtosecond laser 780 micrometer. It can be exposed by laser direct whitening or also by classical photolithography. But here you have to keep in mind it's still a little sticky. It needs to be exposed in proximity exposure. But finally, you have the very stable and highly transparent pattern. Some special application. So special application means mix and match approach. We have customers, they ask, I want to generate smaller patterns beside larger pattern on one substrate. Do you have a material where I can do it in one layer? And for that, we tested it recently. We took a negative MAN 1400 resist, which is an original UV sensitive material, and tested its E-beam sensitivity. And yes, it's also E-beam sensitive. And in that application, some larger pattern, or it was more a case study where E-beam at 50 kV and I-line stepper was used for the mix and match approach, having that kind of different pattern, larger pattern besides smaller pattern. The smallest, the resist thickness was about 200 nanometer, and by EBL 55 nanometers were generated and 350 nanometer by I-line stepper, which is actually the resolution limit of the I-line stepper. And if you want to generate this kind of pattern on a 6-inch wafer, it takes you 10 hours for E-beam only, and 2 hours if you apply E-beam plus 5 minutes for I-line. So much more less time if you have the combination of the two patterning techniques. And once you have exposed it in one layer, one finally development step can be done or is done. This is another example where also E-beam is used for the same resist. Resist thickness was about 500 nanometers. And for the UV, the Muskeliner I-line were applied. And the pattern dimension for the E-beam was 100 nanometer lines. And for the UV, it was 1 micrometer. Yes, and that generated pattern was here used for pattern transfer via dry etching process in the substrate underneath. We also have, or the same material can be done with the MIEPL, which is a chemically amplified material offering even higher sensitivity. So customers have the selection of both or can select between two materials. Here, this negative resist was also E-beam exposed and I-line stepper exposed to generate photonic integrated circuit. Here, a waveguide was generated, a ring resonator, and coupling structures. Finally, the such generated pattern was used for pattern transfer via etching process. And generated pattern dimensions are here and similar as mentioned before. A special application is also some kind of mix and match application. Their inkjet printing with a UV curable material was combined. I will go through very shortly through the process step. First is you have to coat, or you coat a layer, then you generates a small pattern, very small grid by nano imprint. Then you have the imprinted pattern. You put a classical thick UV layer on top, pattern it, and then you want to have a replica of it. You pour a material which can be used for the replication. It can be a hybrid polymer. Cure it, separate it, and then you use it in a PDMS mold. Then you have the original form replicated, and that's the advantage of PDMS is you can easily separate it of any kind of material what you put in the pattern. Then you deposit another material via inkjet printly directly only in the wire, cure it, and release it. And finally, you have that polymeric monolith hybrid and biconvex micro-optical components having, here the smaller grids and here the large lens shape pattern. This is just an example of what's happened by combination of different materials and different techniques. This is another example for a positive resist, MRP 1200G, which is UV sensitive, as I already mentioned. The idea behind here was the generation of hierarchical replace structures by a combination of laser direct writing and laser interference lithography. I already mentioned that's possible with a layer. And the idea was to generate micro and nano scale patterns to be used to reduce frictional resistance on surfaces in turbulent flow. And it's beneficial for surface or any means of transport to reduce fuel consumption and increase speeds. We tested which process should be applied first, and it turned out that it is advantageous to coat a layer, generate via laser direct writing the large pattern, develop it. Then you have the large grayscale or what kind of pattern. And on this kind of pattern, then the laser interference lithography is applied, and a second development step finally leads to the hierarchical pattern. The work was done within the Optimal project. More information can be found on the homepage. And the partners doing the work here was Joanneum and Unigelena. In the pictures show here the grid pattern generated by laser direct writing. By having a closer look, it looks like that. And by having an even closer look, you clearly can see the by laser interference lithography generated pattern on top of the large pattern. So it's possible. Oh, okay, another patterning example. How we can do pattern transfer via PVD and lift off when E-beam is generated. For some cases, the undercut pattern profile is advantage, but not that easy to obtain. For the positive resist, which can be PMMA, having different molecular weight, copolymer or ZAP, it's an acrylate-based resist, a non-chemically amplified resist. It's used as single layer of lift-off resist, and the undercut is generated in a single layer by the use of the backscattered electron. When you expose the layer, the electrons or the beam broadening takes place, leading, caused by scattered electron as well backscattered from the substrate backscattered electron, leading that a higher exposure dose is applied near the substrate than coming from the top. And by having the development, finally you get the undercut profile. That works perfectly for, it works. But sometimes also customers want to use a B-layer system. And yet it's also possible. That's why PMMA having different molecular weight as well the copolymers available. You can imagine you have on top the high molecular weight and below the low molecular PMMA. And once you expose it, PMMA is exposed, then the main chain is cut it off, and leading to much more smaller molecules near the substrate, leading that the first layer is much more faster dissolved than the on top, generating finally the undercut profile. That's a one developer system, but there are also two developer systems. So same principle, but due to the different materials, the recommended developer are different. So some examples are shown here, where either PMMA on LOR PMI is used, or also some deep UV resist on E-beam resists. For the negative resist, yes, I already showed that's possible, but a B-layer approach is also possible. So have the negative resist on top of LOR PMGI. So here you have a defined undercut profile, whereas for the single layer, only its vertical profile. Can be generated grayscale pattern with E-beam, and the answer is yes. So, but also in positive resist. So here's an example for the PMMA, high molecular weight. And once you apply the contrast curve of applying by playing or depositing different dose according to the contrast curve, different kind of or different amount of polymer chains are converted into smaller pieces, leading finally in the developments to a stepwise profile. And this kind of stepwise profile can further be smoothened by applying a temperature. Here's a special application, some kind of complicated pattern where first in PMMA nano imprint were applied by imprinting a stem by a temperature process to have the small grids on top. And then the grooves are then exposed by E-beam exposure and developed, generating here in the wires and the grooves the grayscale pattern while having on top the small grid. By smoothing, by applying a temperature, it's smoothened. And this generated master is then used and replicated with a hybrid polymer to have a more stable master. What about patterning on non-substrate in E-beam lithography? So you can imagine that electrostatic charging is observed, leading in some kind of defects in the resolution. For that, it is recommended to coat on top conductive layer, which could be a metal or which could be a polymer. And for that, MRT is offering two different kind of conductive layers, which are coated on top. MR conductive layer for the MRN 2400, or the discharge for the acrylate, the PMMA for that, or for HSQ can be used. This is not manufactured by us. It's manufactured and provided by Disgem. I'm sorry. And yeah, we distribute it in Europe. But if you're interested in that, please ask Disgem. They would be happy to provide it to you. Some patterning examples are shown here. General aspects for patterning. I think I have to proceed a little bit up. Oh, okay. These are the process flow for processing of resists. Clean room conditions, for sure they are important. For thin resists, it's not that important, but for processing of very thick resists, it's important to have stable clean room condition as mentioned here. if it is not the case, you will have an influence, or this influence the film thickness, the adhesion, the developing time. Also, if is to higher humidity, the bubble formation during exposure, stress and cracks. So it's always recommended for thick films have stable and clear clean room conditions. We provide the resist, and the resists are coming with a processing guideline for the photoresist as well for the ancillaries. Substrate pretreatment. Why? Improve of adhesion by chemical reaction or adaptation of surface energy. It should be clean. Oxygen plasma, ozone plasma activation is recommended to apply to be sure that no humidity and no organics on top. A bake also for moisture removal at higher temperature. So that's recommended to apply. Sometimes also a solvent rinse is sufficient, IPA or PMGA as pre-wetting. And depending on the kind of resist, also some adhesion promoter are recommended to be used, such as HMDS pure or HMDS solution in organic solvent, or Surpass 3000, 4000, which are waterborne cationic materials, followed by an IPA rinse and then apply the resist. So please check always the guideline. There are recommendations which process is recommended for which resists. Layer preparation, as I already mentioned, spin coating is the most common. According to spin speed curves, apply the spin speed. For thick layer and remove of the edge bead is recommended by high volatile solvents during spin coating that the resist is transported away very fast. You also can apply double coating, but for thick layers and edge bead remove is recommended before coating the next. Spray coating is recommended, preferred on non-planar substrates, otherwise you can spin coat, and requires sometimes a solvent-modified resist solution. Inkjet printing, already mentioned as material-saving methods, requires also solvent-modified resist solution. Doctor blading dip coating, also preferred for non-planar, non-spin coatable substrate, may also require solvent and viscosified modified resist solution. And lamination of dry films. It's a rather easy, fast process. This is some kind of tabletop laminating equipment. Their temperature and pressure and speed can be tuned. This is by opening the tool. There are heatable rolls. It's a rather fast process. The waiting time after layer preparation. For thin resist, it's not required. For thick, it might be required. Check the guideline. Soft bake. Why? To evaporate the solvent and to improve the layer homogeneity. Hot plate or even oven could be possible. For thick resist, temperature ramps are recommended. Oven bacon requires sometimes longer time than time for hot plate, sometimes also 5 to 10 key higher temperature. Waiting time after soft bake. For thin resist, it's not required, not necessary. For thick resist, yes. For the positive resist, since they need the water for the chemistry. And it's for different thickness recommended to wait for a certain time that the water can go into the layer and allowing the reaction. For negative resist, for especially the epoxy resin-based, relaxation after a baking step leads to less stress. Pre-exposure bake, not required for thin resist. For very thick resist, it may require if you store the layer. So we have customers, they ordered coated SU8 layers. Or also we send out coated D&Q Novolac resist. And if the customer wants to start the exposure, then after a certain time for shipment and storage, pre-exposure bake is recommended. We give recommendation for that. Exposure. Resist absorption should correspond to the emission wavelengths and energy of the used equipment. That's very important. Exposure dose adaptation, broadband exposure versus single wavelengths. You can see of the positive resist, if you have mask aligner broadband and use I line, H line, G line, you have a certain dose. But if you have only I line or only G line, you have to apply the 2.5 to 3 times higher dose for single wavelengths and exposure than for broadband exposure, just to keep in mind and to think about that. Then, okay, lasers and LED exposure is also possible. LEDs offering a broader range, while laser direct or has a clearly monochromatic light, meaning that with laser, the dose is slightly higher than for LED because of the broader band, emission band. Low laser power is preferred, or multiple exposures, and to have sufficient time for photochemical reaction in the layer, and to avoid overheating, and for the positive resist that the nitrogen release in thick layers is allowed and not leading to big bubbles. Shorter wavelengths enable smaller pattern resolution. And as already mentioned, for thick D&Q Novolac resists, the longer wavelengths allow to generate a deeper pattern depth because of the lower resolution, as I already explained before. Post-exposure bake, it's mandatory for chemically amplified resists because a chemical reaction takes place during that process. So it's for all epoxy-based, but also for some deep UV resists. Please check guideline. Post-exposure bake may advantage for thin layers, also for non-chemically amplified, for the positive resist, to improve resist onto substrate adhesion, and to reduce standing wave effects, especially when monochromatic is exposed. Waiting time after PAP for thin resist not necessary. For very thick resist, it's required for each baking for SU8, so to avoid stress and crack and delamination. A ramp process is sometimes recommended, and let relax fully to room temperature before starting the development. Development rinsing, yes, it's recommended mainly at room temperature or at least at same fixed temperature. If the temperature is different, then the development behavior or velocity is different. So please ensure same fixed temperature. What can be used for the development? Weak alkaline, it can be TMAH. Sodium hydroxide or kalium hydroxide for the Novolac-based resist. So the question is, do you want to have a metal ion containing developer or not? That is the decision. And there are also sodium metasilicate phosphate developer available on sensitive EJ aluminum containing substrate. Solvent-based developer for SU8 or for acrylate-based materials such PMMA copolymer or the hybrid polymer. Then the rinse in water for water-based developer or rinse and stop in solvents. And then the resist pattern drying by spin dry or by nitrogen flow. Post-development bake may advantage depending on resistant application to increase pattern stability for pattern transfer. Ramp processes are beneficial, less cracks and less reflow. Check guideline. And for positive resist, grayscale patterns reduce surface roughness. Removal, and the pattern transfer is run for the removal. Can be done, solvent or alkaline based at room temperature, or if required, for SU8 or other strongly cross-linked materials or crusted resist pattern, also at higher temperature. Depending on the resist and on the used remover. It can be also ultrasonic assisted done. Sometimes it takes time for HI4HC8. And then the rinse in water or solvents, drying, besides the wet removal, also dry removal, pure oxygen plasma can be applied. FAQs. I only have few FAQs. Let me check the time. Okay. Why are many resists red in color and some are clear? It depends on the raw materials. You can imagine PMMA is a poor polymer, but if you need to have a material that absorbs the light, there is a certain material having a color. Otherwise, it does not have an absorption, and that makes components red in color. So the Novolac resin is slightly yellow, and the photoactive compound as well. So leading to a colored resist. Also, sometimes there's a color, a dye added to make more visible the contrast between exposed and non-exposed areas. What makes a developer a developer? Why can IPA be used as developer for PMMA as well as stopper? So first, it should dissolve, the developer should dissolve the desired resist area. It should not attack one area, but dissolve one specific area. For PMMA of different molecular weight, so there are solvents which dissolved each PMMA having different having molecular weight. They are non-solvent, so IPA, water, TMAH, ethyl lactate is a non-solvent for PMMA, and indifferent solvents having hardly dissolution force for PMMA. And it's recommended to use a mixture, or they found out experimentally, to have a mixture of indifferent and non-solvent to develop the PMMA and stop with a non-solvent. That's clear. And the mixing ratio of a indifferent solvent and non-solvent allow to tune the developing the velocity. There are MEPK IPA of different ratio available, leading to different developing time and throughput. So that's a clearly defined ratio of indifferent and non-solvent. What about the dry etching stability of acrylate-based resist? So resist chemistry for high etching stability, there are main rules. If you have aromatic groups in the polymer, in the resist, you have a higher dry etching stability than for aliphatic main chain. And PMMA is purely aliphatic, having itself a low dry etch resistivity. You can add aromatic group. This is done for the Caesar as well for the ZAP, leading to a higher dry etch stability. And there are more general information. The meaning also to increase the carbon H ratio. So it's the same. So for aromatic. So having a lower H ratio, also low H, increase the carbon, leading to a higher dry etch stability. That's an empirical group, and that's the reason behind the different dry etch stability. TMAA versus sodium and kalium based developer. I already mentioned metal ion-free, metal ion-containing, and TMAH-based developer generates lower surface roughness in grayscale litho. So because of the higher volume of the tetramethyl ammonium compared to the smaller calcium or sodium. Resist shelf life, expiry. What are the properties which may change? Our recommendation is always draw as recommended. And after passing that shelf life or coming to the end of the shelf life, the viscosity may change, resist thickness, color. It's a slowly process. It's not a sharp process. It's a slowly process, but this can lead in higher exposure dose or change exposure dose, developing time, resolution. You can, in principle, use the resist after passing its shelf life, but keep in mind the parameters and these may change. For more information, you can have a look on our homepage. We have product information and flyer for download. We also have the FAQ session. You can have a look. We have a tech blog and also how to use videos. So how to apply a grayscale resist, how to apply a dry film resist. You can check on that. You are also invited to take part in our MRT webinars. It takes place once a month. The next is already scheduled on 19th of February. It's for European time. I'm sorry, for you it's, I guess it's in the night. But any case, you're invited. We have some white papers for download. Yeah, for sure, processing guideline on requests for all our materials. With this, I'm coming to the end of my presentation. Hopefully, I was able to present materials as well, the chemistry behind, what are not only available from MRT, also from other, and for which are available for E-beam, standard UV and laser lithography, for conventional pattern transfer processes, and fast and contact prototyping. Hopefully, I was able to give you some examples for thin, thick film, grayscale lithography, mix and match techniques, one photon and laser interference lithography, generated materials. And I've shown only shortly explained what you can do or our hybrid polymers can be used. With this, I would like to come to the end of my presentation. I would like to say thank you, and I'm open to your questions if there are any. Thank you.
Thank you very much, Anja and Arne and Christine, for this very nice presentation, walking us through different application cases and also answering our frequently asked questions. So thank you very much.